Hello. In today's lecture, we'll see reconstruction of continuous time signal from its sampled version, the concept of aliasing, and precautions to take in case of aliasing. So in the last lecture, we have seen the spectrum of sampled signal. This spectrum we have derived a formula for the spectrum. X del of omega is equal to 1 upon Ts, and this spectrum shifted version of the spectrum. So this spectrum is drawn. This is the original spectrum. Its shifted version by 2 omega s, its shifted version by minus omega s, like this, so on both the sides, on this side as well as on this side. So we have seen that this is multiplied by a factor of 1 upon Ts. So how to get back the continuous time signal? Because of sampling, these images are occurring, but we want only the original spectrum back. So to get this spectrum back, we'll use a low pass filter. Okay, we multiply this signal with this signal. So these two spectrum are multiplied and we get this spectrum like this. So observe here, this amplitude of this low pass filter is Ts. So this multiplied by 1 upon Ts, this becomes 1. So we get back our continuous time signal from this spectrum of the sampled signal, or you can say we can get back sampled signal by passing this sampled signal through a low pass filter. This is shown here. Reconstruction of continuous time signal from its samples. So we have seen this process of multiplying x of t with s of t. Here we get the sampled version of the signal x del of t. X del of t is the sampled version after passing it through a low pass filter h of omega with cutoff frequency omega c. Omega c is somewhere, so its value is omega s divided by 2, sampling frequency divided by 2. So it is in the middle here, omega c value. So we get this continuous time signal x of t here. This is spectrum of the sampled signal x del of omega. This is spectrum of this x of t, recovered signal. X of omega is the spectrum of this recovered signal. So this is multiplication of x del of omega into h of omega. So this is how the reconstruction process is there. So we'll see, I've written here case 1. So case 1 is a very normal case where sampling frequency is chosen such that there is a gap, band gap between these two. This maximum frequency value and this point of the image. So these 2 points are not touching each other or not interfering. These 2 images are not interfering within each other. So we can write this case. Drawn these points like this, omega s. So width is same, o minus omega m to omega m. So this width is also twice of omega max. So this point is omega s minus omega m, and this point is omega s plus omega m. So we can write in case of case 1, when the signal can be exactly recovered, at this point omega s minus omega m, this point is greater than this point, this value. omega s minus omega m is greater than omega m. So this inference we drawn from just observing these 2 points. So these 2 images are not mixing with each other, means this image is not interfering within this original spectrum. So by this, the value of sampling frequency becomes greater than twice of omega m. So this is one condition where some gap is there. Okay, you can say guard band is there. So in this case, recovery is possible. Recovery is possible. So here the value of sampling frequency is much greater than the required value. So this case is called as oversampling. Now we'll move on to second case, where the choice of omega s is such that these 2 spectrum and this image, these 2 are touching at this point, means this point omega m and this point for this spectrum image omega s minus omega m, this point, these 2 are same in this case. So for the case 2, the points are same. Omega s minus omega m is equal to omega m. So omega s is equal to twice the omega max. So in this case, you can use a low pass filter here and take the original spectrum back. So exact recovery of the continuous time signal is possible. So we'll write here recovery is possible. So this case is, we can call it as perfect sampling. Now the third case, see here the third case, here the value of omega s, you can compare this by this line, blurred line. That this value of omega s is less than this value. So this image is interfering now the original spectrum. So now this point omega s minus omega m is lower than omega m. Okay, so this red area is called as aliasing effect or called as spectral folding. So because of this, the spectrum get mixed into that, and the spectrums are becoming like this. Spectrum is mixing. Okay, so the original shape of the spectrum of the sampled signal got destroyed in this case. So using a low pass filter, you cannot get the original shape back. So this is the effect of aliasing, and as we are not retaining the shape here, so we can't recover the signal back. The continuous time domain signal, it can't be recovered in this case. So this is a case of aliasing. So we'll write here the case 3. Case 3 is aliasing. Here the point omega s minus omega m is less than omega m, this point. So because of that, mixing occurs and exact recovery is not possible in this case. So omega s is less than twice omega m. Recovery is not possible. And this is also called as undersampling. This is called as undersampling because omega s, the sampling frequency, is chosen less than the twice of maximum frequency present in the signal. That's why it is called as undersampling. So wherever the recovery is possible in this case and in this case. So combining these two conditions, we make a condition. Combining these two, omega s is greater than or equal to twice omega m, that is the maximum signal frequency. So this is a relation for sampling theorems. Hence this relation is proved now, and the concept of aliasing is also explained here. So how to avoid this effect of aliasing? So to avoid this effect of aliasing, if we are going to choose a sampling frequency like this, suppose in this signal spectrum where we have chosen this omega s value like this. So spectrum is folding at a point, spectrum folding point, this point is omega s by 2, omega s by 2. This is spectral folding point. So you can use a low pass filter before signal sampling, that is called as low pass pre-alias filter. So the extra component higher than this value, cutoff filter having cutoff frequency omega s by 2, so that values greater than this point will be cut off and the signal will be band limited to a value omega s by 2, and you can pass through then you can sample this signal to get a aliasing free signal spectrum, you can say. So this was the concept of aliasing in sampling. Hope you understood this whole process of sampling and what are the effects of choosing a value of different values of sampling frequencies. Thank you.